see if got audio here. Would somebody mind closing the door, please? Would somebody mind closing the door? Thank you. All right, I sent out that homework assignment and I've been asked to discuss the first problem, which was not the first problem, the number 5, right? Find the inverse of x. Yeah, I'll do 6 with this. All right, so we want to find the inverse of this function. So last class, what we were given were a set of steps. The first thing was to replace the f of x with y. The next step was everywhere we see an x, everywhere we see an x, put a y. Everywhere we see a y, put an x. Yes. Yes. This is number 5. You got the wrong what? There was problems 1, 2, 3, 4, 5, and 6. So number 1 had find the inverse. Number 2 was show that f of g of x equals g of f of x. So first thing was to find what we think is the inverse. So I switch my x and y, and now I solve for y. So right now I have a y cubed plus 1 on the right side, so I would subtract 1 from both sides. That would leave me with x minus 1 equals y cubed. And then if I don't want y cubed and I want y just by itself, I would take the cube root of both sides of this equation. So I take the cube root of x minus 1 equals the cube root of y cubed. So that turns out to be, I'll put the y on the left side, y equals cube root of x minus 1. So we have solved for y. So the last step is to replace y with the f inverse notation. So that's what I'd be looking for on number 5. So we believe that the inverse of this function is the cube root of x minus 1. Any questions on that? Nope, that's it. Because it's a function, right? So no setting it equal to 0 or anything like that. Just write what the function is. Yes? Yeah, that's number 6, right? So part 6, or number 6 of the homework was to, well, what did it say exactly? It said verify your answer in number 5 by showing f of g of x equals x and g of f of x equals x. So here's the way we do this. For number 6, we would say, all right, the original function we started with was x cubed plus 1. We just found what we think is the inverse, right? But since I'm checking it, I'm going to call it g of x. All right, that's the function we just got. But we're going to call it g of x until we verify it. Once we verify it, then we can officially stamp it as the inverse. So the first thing I need to show, right? The first thing is to show that f of g of x equals x. That's what I need to show. So that means I need to figure out what f of g of x is. So f of g of x means you take f, you plug in g of x. That means you take f and you plug in whatever g is. And g is that cube root of x minus 1. Is that okay? And then now I take this and I plug it into f, right? Now f, if you go up to the f function, if you plug in x, you're going to wind up just cubing it and adding 1, right? So I'm going to take that highlighted yellow part sitting there, the cube root of x minus 1. I'm going to plug it in, so I'm going to take it, cube it, and add 1. So I'm get rid of the f now and actually apply the function. So I'm taking the cube root of x minus 1. I am cubing it and adding 1. Does everyone see that all I've done is taken this and plugged it in like I would right here? So it's getting cubed and adding 1. Does that make sense or not? Is that all right? Yes. Okay, so, okay. So what happens when you cube a cube root? They cancel out. Just like when you square a square root, it cancels. So you have x minus 1, but then you have plus 1. That gives you x. And that is exactly what I was trying to show, was that when you go and do that composition, f of g of x, you get x. Now you're not done, because now you need to show it the other way. You have to show that when you reverse it, g of f of x, you also get x. So this time I take the g function, inside of it I'll put f of x. That means I take the g function and I put in the function f, which was x cubed plus 1, right? But g, when you look back up at g, where's g? Right up there. You zoom out just a little bit. When you look at g, if you plug something into g, that green I put up there, then it gets put underneath this cube root right next to a minus 1. So I'm going to take that black x plus 3, I'm sorry, x cubed plus 1, I'm going to put it right next to a minus 1, and I'm going to take the cube root of the whole thing. So this becomes the cube root of the x cubed plus 1, but then I have to subtract 1. So that is getting plugged in right there. Does that make sense? Now you have to kind of do what's underneath that root first. X cubed plus 1 minus 1. Yeah, the plus and minus 1 cancel, so you're left with cube root of x cubed. And the cube root of x cubed is just x. So it verifies. Four? Which part of it? The verification or? Okay, tell me what you want to tell me what you think you got for the inverse?
For your inverse, it would be x plus 1.
You got the same exact thing? Yes? Anyone else get the same thing? Yes? Okay, so potentially, here's what we had set up. We want to check that x plus 1 or x minus 1, we think that the inverse is the same thing. I haven't done this, so I'm not sure if this is right. We'll see. We're going to find out right now if they're inverses. So first thing I'm going to check is whether or not f of g of x is x. Right? I want to show that. So that means I take f, inside of it I put g. That means I take f, inside of it I put g, which is x plus 1 over x minus 1. And then I'm going to take that whole thing in blue and be replacing my x's, right? Everything in here goes in to there, into those two x's, right? This is going to be kind of complicated looking. I'm going to have x plus 1 over x minus 1, but then that whole thing plus 1, then divided by x minus 1 over x plus 1, but then minus 1. So that's what it looks like when you take that g function and plug it into the f function. Well, yeah, what happens here? You can't do anything. What I did in class last time was I said try and get like a common denominator or something. And this one works very well, different than what we did before in the previous class. So that's why this is probably a little confusing. So let me do it this way. I had a feeling we'd have questions about this one. So let me just look at this numerator for a second, okay? I'm just scratch work here. I'm just going to write it down real quick. What I'm going to do is try and put these two things together. But to put them together, they have to have the same denominator, don't they? So they both have to have an x minus 1 in the denominator. So what I'm going to do is take this 1, which is really a 1 over 1 right there, and I'm going to multiply the top and bottom of it by x minus 1. Just like you do when you have, numbers in denominators. You have to multiply a fraction, one of them, top and bottom, to get the same denominator. That way it's still a 1, right? So what I'll get here is x plus 1 over x minus 1 plus x minus 1 over x minus 1. Do you all agree that's the exact same thing? Right? The x minus 1 over x minus 1 is really a 1. But since they have the same denominator, I can just put them together, which means I take the numerator, x plus 1, and I add to it x minus 1. So just put all those together, and what do you get? You're adding the x's. Add them. 2x. And then you take 1 and subtract 1, and you get nothing. All over x minus 1. Okay, so that's just what the top is, right? Is that okay? All right. Now, look at the bottom. The bottom one, let me do the same exact thing on the bottom one. I'm going to take my x minus 1 over x plus 1 minus 1, but I'm going to rewrite that 1 as what? 1 over 1. And what am I going to put in there? X plus 1 over x plus 1. So this will become x minus 1 over x plus 1 minus x plus 1 over x plus 1. So again, that 1 is really that. Now be extremely careful here because you are subtracting, right? You see the subtraction sign in between? So what happens here is this. You're going to take x, you're going to subtract x, which means you have what? X minus x is nothing, right? So I'm not going to put anything. Then you're going to take negative 1, right? And subtract 1. What's negative 1 take away 1? Negative 2. So you get negative 2 over x plus 1. Nasty, right? I know. Is that all right? Well, let's see what happens. Hold on. Any questions on that, though? I'm going to go back up to where we were up here. What was that numerator? What was this whole thing up here? It was 2x over x minus 1. And the whole denominator was negative 2 over x plus 1. Agreed? You agree with that, though, right? Okay. Now, I need to move down. Actually, I think I'll go to a new page. This right here, I'm going to work on that, okay? 2x over x minus 1 over negative 2 over x plus 1. Now, let me show you something because this is really important, all right, what I'm about to do. Remember good old days when we had fractions like 3/4 divided by 5/3? You were told that you could switch this to 3/4 times 3/5. That division is the same as multiplication of the reciprocal. So you keep your 3/4, but then you flip this one, right? Remember that? Okay. Now, the way I wrote this over here, 3/5 divided by 5/3 is kind of like elementary school. You use that little division symbol. In reality, what it really is 3/4 divided by 5/3, isn't it? I mean, that's what 3/4 with that division symbol 5/3 means. It means takes 3/4 and divide it by 5/3. Do you see that we kind of have the same thing here? We have a fraction on top and a fraction on the bottom. Just like here, we have fraction on top, fraction on bottom. And what it really turns out to be is that bottom fraction, 5/3, flipped up and put right next to the 3/4, isn't it? I'm taking this 3 and putting it up here, taking the 5 and putting it down here, and then multiplying across. That's what it really turns out to be. So this one is going to be the top, 2x over x minus 1, times the bottom one flipped over, x plus 1 over negative 2. Now, how do you multiply fractions? Straight across. Now, I have two terms on the top, and then over here I have two terms, so I'm going to put them in parentheses. And now distribute through. So what's 2x times x? 2x squared, and then plus 2x. And on the bottom, what do we get? Negative 2x and plus 2. Yes? Okay. Look at your numerator. Can you GCF the numerator? What can factor out? 2x. And what's left? Plus 1. Oh, wait, hold on. No, that's right. What do you get on the bottom? Can you factor anything out of the bottom? You pull negative 2 out and you're left with x minus 1. And the 2 and the 2 cancel here. I still have, you know what? I don't think that's the inverse. See, what should happen here is everything should cancel out. We should just get an x. Right? Look, we're trying to do composition, right? F of g of x, and we're trying to show that that's x. If we can show it's x, then we're done. But this is not turning out to be x. So let's see. How many of you actually tried number 3? I mean, and you got number 3, you found an inverse? And you got the same exact thing, the same function? Okay, let's verify that. Because I'm skeptical right now. Don't be mad. Don't be mad. Okay, there was the original problem, number 3. The first step is to replace f of x with y, right? Now switch x and y. Now solve for y. So how would you solve for y here? Multiply both sides by y minus 1 here on this side, y minus 1 here. Now, these cancel on the right side, which leaves me with y plus 1. On the right side, I distribute my x through. So I get xy minus x. Now, what did I tell you to do in class after this? All your y's on one side, all your x's on the other. So I'm going to have xy minus y on the left equals x plus 1 on the right. Yes? Okay. Now GCF y, left with x minus 1 equals x plus 1. Then divide y equals x plus 1 over x minus 1. That's the same function. Okay. That worked. Any questions, though, on that? That means the unthinkable has happened. No, I think I've made a mistake. No, I mean, up here, somewhere in my algebra, let's look at this. Let's just verify that I plugged. Oh, I see it right now. I see it right now.
Did you need a 1 there?
No, look what I did. Hold on, let me take this off. I was supposed to plug this into that function, right? Up there. So I put it right there, and I put it right there. No, I didn't. It's backwards.
Oh.
I knew
That's plus
it.
and minus.
I saw it too, and I
You should have said
put it the right way,
something.
and then I erased it.
Do y'all see what I did? This right, these should be the same exact things.
That's a hell of a party plan.
Well, I'm gonna fix it. What? Just try and see if you can follow this. All right. Should I just start it all from here now, or what? What would you prefer, or just me go in there and change the signs?
We came this far.
I'll fix it. We're all human, right? Okay, was it, it was +1 on top? Sorry about that, everyone. Usually everybody wants a bonus after I make a mistake. Well, does that mean that we can get points when we make mistakes? Okay, that's correct, right? Please verify. Now, this actually works out a little bit nicer now. Because these are the same, you can do exactly what I did last class, which was, does anyone remember? Multiply top and bottom by x minus 1. So I can multiply the entire top by x minus 1, the entire bottom by x minus 1. Now, the reason why we do that is because when you distribute this to this, what will happen? The x minus 1s cancel, and you're left with just the x plus 1, right? And then when you distribute this to 1, you get what? Plus x minus 1. Right? 1 times x is x. 1 times -1 is -1. Now on the bottom, you do the same thing. Distribute here to here. The x minus 1s cancel. You're left with x plus 1. And now be a little careful here. Yep. When you go here to here, you'll get minus x. And then minus a minus is going to be plus 1. Much nicer. So on top, you get 2 x's. The 1's cancel. On the bottom, you get x's cancel. 1 plus 1 is 2. And then your 2's cancel, which is x. But that was a fun exercise earlier, wasn't it? That was fun, the algebra. The algebra of complex fractions. That's what we don't spend a lot of time in college algebra on complex fractions. But if, like again, if you were going to take 1414, the other college algebra, they spend a lot of time on complex fractions. All right. Hey, that's life. Happens. Now, do we have to show g of f of x? They're exactly the same setup because they're the same functions, so you wouldn't have to show it again. Okay. All right. Well, I hope that the homework, somewhat, I guess, made sense. Other than that issue. What I'd like to start today is exponential functions. Now, this word exponential comes from the root word, exponent. Exponent usually meant power, right? Like the power on something is the exponent. Remember that? Yay or nay?
Yes,
If I write down like a raised to the b, or you know what, let me do it the other way. B raised to the a. This bottom part was called the base. The top part up here was called the exponent. So we are going to look at functions that involve exponents, but it's not just any function. Where, like, it seems like I always hear the word exponential when I'm watching the news. You know, like whenever you are watching something on TV and they're trying to illustrate that something is growing very rapidly or going away very rapidly, they usually use the word exponential, and it's misused all the time. Yeah, it's growing exponentially, you know, la la la. But that really, they just say that to make you understand that it's growing fast, right? I mean, is that your interpretation when you hear it on news or some radio, right? Exponentially means fast. Well, it turns out that that is the case most of the time. So somehow it's connected to growing fast. Let's take, I think, an example is always a good thing to start with, and then we'll get into like defining what they are. So we're going to do our first example to help us kind of motivate this whole idea. This is what I'll call the bacteria example. Okay, has anyone ever taken like a biology class and used a petri dish before? Petri dish is a little plastic dish, like a little saucer. It's sterile, meaning there's nothing in it, right? There's no organisms in it. It's just sitting there. And what you do is you put something in there, like you throw a bacteria in there, and you close the lid, and then you come back later and you see what happens. And then maybe like a week later, you look in there like, ooh, whoa, that's nasty. It's all fungus or whatever, like a chia pet, yeah. So we're going to do this example with the idea of like a petri dish, all right? We're going to start out like this. We're going to make a table, right? And on the left side of the table, we're going to put what day it is, and then, or I should say number of days. And then on the right side, the number of bacteria. And let's say that I am able to calculate some data. So I start on the first day, or not the first day. I start out, I grab a petri dish out of the lab, open it up, and I place a single bacteria into the dish, right? What I would say is that at day 0, I have one bacteria, a single one. And let's say that I come back and I'm able to measure this. Now, this might be hard to do, but let's just say that I'm able to measure that one day later, so 24 hours later, I go in there, I measure again, and I now have 2 bacteria in that dish. So it has doubled itself in one day. Now it depends on the bacteria. It might be, it only takes 1 hour. It might be, it just depends on what it is. In this particular bacteria, it's somewhat slow growing. It doubled itself in one day, right? And then let's say I come back in a day later. So on day 2, I now have 4. So again, it's doubled itself, right? Now I'm going to draw a picture next to this illustrating what's happening. Ooh. This is a single bacteria, right? That's day 0. I put him into the dish. And then one day later, this bacteria has doubled itself, right? And now there are 2 bacteria. One day later, each of those has doubled, right? So you double. It does, kind of. And you have these guys, now they're starting to be straight-faced because they're starting to, think we're all the same. We're not unique, right? Like a bunch of lemmings. Yeah, well, he's a mutant, I guess. So now they double again, right? And that keeps happening, right? So what would our next table entry be? On the 3rd, we would get 8. And then on the 4th day, we would have how many? 16. So all you're doing is every time you go to the next day, you're doubling the number before, right? Well, that's all fine and dandy. But what if I ask you now, what happens on day 10? How many do you have in there? You see, to get day 10, wouldn't you have to first get day 5? And then day 6, and then day 7, and then day 8, and then day 9, and then day 10. So it would take a little bit of work, wouldn't it, to go get that? So the question is there a function that when you plug in, so when your input is the days, it spits out the number of bacteria, right? Is there a function that describes this sort of behavior? And the answer is yes, but I want us to first think about it, right? Do you see that it's useful for us to have the function? Because if we can have a function, we don't have to go and make the whole table. Like if I asked you what, after 3 weeks, how many bacteria are there? You wouldn't want to go through, all the way 4, 5, 6, 7, 8, 9, 10, all the way out 21 days. You just want to take 21, plug it into something, and get an answer, right? Everyone understand the question? Okay, so let's see if we can figure out a pattern other than the fact that it doubles every day, a pattern with each of those numbers that we have in the right column. Does anyone notice what those are? On the right column. I mean, I know they're all even numbers. That's fine. Are they all squares? 8's not a square. And also, well, yeah, 2's not a perfect square either. 4 and 16 are. They're all multiples of 2. Is 1 a multiple of 2? Okay, so let me force your eyes here. Do you agree that 2 here, the first one, right, the second one, is 2 to the first power? Do you agree that 4 is 2 to the second power? Do you agree that 8 is 2 to the third power? Do you agree that 16 is 2 to the fourth power? Yes? And isn't the number that I'm plugging in here just the number of days? If this is true, then what about that first one on day 0? Is 1 equal to 2 to the 0 power? So you could grab your calculator if you wanted to check. But we do have a property of powers that says anything to the 0 is 1, except 0 itself. 0 to the 0 is undefined. Yep. So yes, 2 to the 0 is 1. So every single one of our days follows that pattern. Even the day 0 follows that pattern. So that means on the 10th day, right, I would have 2 to the 10th, which I would need my calculator. And let me mention now, you should have your calculator with you every day, probably for the rest of the semester. Your phone is not acceptable on a test for a calculator. So bring this, right? Bring your calculator. You do not want to be coming to the test and that be the first time you're ever trying to use your calculator to do this stuff. Because everyone's calculator is different. The way you type things in is different. So if you have your calculator, try to figure out what 2 raised to the 10th power is. And if you can't find it on your calculator, and you have your calculator in your hand, but you can't figure it out, then let me know, and I can help you. You should get 1024. Are y'all with me? I don't have questions. So let's just ask now, what would happen 21 days later? All right? 21 days later, I'd be doing 2 to the 21st power. 2 raised to the 21. 2097 152. So you now have 2,097,152.
That's a shitload of bacteria.
Well, it's a lot. Now, do you see why they say exponential growth? I mean, it went in 3 weeks, right? In 21 days, it went from 1 to 2 million. Now, let's just try to see what happens if we do a month. And let's just go like 30 days, okay? What would happen if you try 30? Just a couple of days later. Now, how many of you on your calculator are getting something like this? 1.0737, and then like E. Anyone getting that? E? No? Well, are you getting that? What does it say? E what? I'll address that in a second also. What do you get? You got 1.0737 times 10 what? Does it say? Who said that?
If I get 2 to the 40th, I don't
Well, 2 to the 30th.
2 to the 30th.
Oh, but at 2 to the 40th it does?
It says 1.09 and then
Okay, hold on. Let me do the 30th first. Is anyone getting an E when they do 30th? You no? Nobody? Okay. All right. Nobody's getting an E. So this is the number I get. 107,374,1824, which is, what is that?
1 trillion.
One,
Right? Because it's billion. Was it zillion or trillion?
it's gazillion. What is it? Isn't this million right there? What comes after million? Billion. So that's a billion. So you have a billion bacteria there. Now, should we try 40? Let's try 40.
40 is where I get 1.099512.
Okay, you're getting 1.09 what?
99511.
9951628, and then what does it say? E12. Anyone get something other than E12? Times 10 to the 12 means the same thing. What E means is basically E. That's a big number. That's what it means. No. It means it means take your decimal point and move it 12 places to the right. If you move it 12 places to the right, that's the number. All right? So I would need to write it out. It would come out to be 1099516. Oh yeah, 1628000. That should be it. Let me just count it real quick. Started here 1 2 3 4 5 6 7 8 9 10 11 12. Yes, okay. That works. So that's the number. Let me put some commas in here. All right, so what's that? What number is this? This is millions. This is billions. This is trillions. That's not even, that's 1/15 of the national debt. The national debt is 15 times that. Trillions of dollars. I didn't mean to do that, but you know. Okay, so it's growing pretty fast, right? Do you even want to attempt a year? I dare you to put in a year on your calculator. Let's go 365 days. It will break your calculator. Oh, mine didn't overflow. Mine didn't overflow, but yeah, most calculators are going to go, most calculators will freak out on that. Error, overflow. Yeah. It's just the number's just too big. It's just too big for the calculator. All right. Let's get back on track here. So here's what we have. We know that for this bacteria problem, the function that we use would be 2 to the x, right? Does that make sense? 2 to the x? This is the first example of an exponential function. I want you to notice where the variable is. Where is the variable in this problem? Where's x? It's in the exponent. Thus the name exponential function. Exponential functions are functions where your variable is in the exponent. Now I want you to look at that versus this function. That function we've studied. That's, what is that? X squared, it's a parabola, right? Now the difference between 2 to the x, which is what we have on top in the red, 2 raised to the x, versus x raised to the 2, is that the top one is exponential, the bottom one is a polynomial. It's a quadratic function, but remember all quadratics are polynomials? So I guess maybe a natural question would be, they both grow, right? Which one grows faster? So what if we would have made a table for x squared instead? If we would have plugged in 0, what would we have gotten? 0. We plugged in 1, we would have gotten 1 squared would be 1. 2 squared would be 4. 3 squared would be 9. 4 squared would be 16. And then we could keep going, right? Let's try 10. What's 10 squared? 100. What's 30 squared? We did 30, right? 900? Is that right? No. 900. And then did we do 40 a second ago, right? That'd be 1600. So, do you understand what I'm doing? Exponential is much faster, right? Much, much faster. Now, if I put the exponential table next to this one, 0 we had 1, 1 we had 2, 2 we had 4, 3 we had 8, 4 we had 16, 10 we had 1024, right? 30, I mean, we were off the charts. Well, not off the charts, but we were getting really big really fast. In the beginning, they're kind of close, aren't they? They're kind of close in the beginning, but then as soon as you start getting past like about 4 or 5, the exponential function just takes off, right? Compared to the x squared. So it's much more rapid growth. They are not the same function. That's the main thing I want you to take away from this. 2 raised to the x is not the same as x raised to the 2. All right, let's do another example. What about having, again, a bacteria problem? Well, you know what? I'll save the next bacteria. Let me do the folding paper problem. Any of you ever watch Mythbusters? Okay. Yeah, where they do the folding of the paper. So in Mythbusters, what they were trying to do is test this myth that you cannot fold a piece of paper over itself half, and then half again, and then half again. Like there's a maximum number of folds that you can do before you can't do it physically. I think they got 16 or 13. And they basically had like this like football field length piece of paper, and they folded it and they ran over it with a steamroller and kept on rolling over it, steamroller, and they kept on doing it. And there is a maximum, no matter how big the page is, there's a maximum, and it's either 13 or 16, I forget. But let's look at why that's happening, okay? So what I'm going to do here is I'm going to look at the number of folds, the number of folds, and then the thickness. And in the thickness, I'm going to be putting it in the number of pages. What I mean by that is, if I don't fold a piece of paper, how thick is it? 1 page thick, right? It's just my 1 page thick. So no folds is 1 page thick. Now, if I fold it 1 time, how thick is it now? 2 pages thick. If I fold it again, what is it? You've got the 2 that you had before, now 2 more, so you have 4. If I fold it again, third fold, I'm basically doubling how many I had before, aren't I? So now 8. If I go again, 16. Go again, 32. Follow? Now, they claim that it's either 13 or 16. So let me go out to 13, and then I'll put 16 also. Now, does everyone recognize this is the same exact function we just did? This is still 2 to the x, right? All of these are powers of 2, right? So what would 2 to the 13th power be? 8,192. And then 2 to the 16 is 65,536. Let's just go with the 13 to start, okay? Let's just think about that for a second. Let's say I start with a page, right? It's 1 page thick. I fold it once, it's 2 pages thick. And then when I fold it again, it's 4, right? Every time I fold, this crease, right, in the middle, that fold, that crease right there is at least as thick as the number of pages I have, right? That crease, that thickness. So look at 13. If 13, I'm 8,192 pages thick. What does an 8,192 page book look like? I mean, what's the thickest book you have in your backpack? Maybe 400 pages, right? Imagine 8,000 pages. So 20 books stacked up, something like that. That's the thickness of just that crease. Do you understand? Like you're running out of paper. You don't physically have enough paper to come around and fold around the previous thicknesses. Not to mention that the fold before that had to be so many thousand thick. So it just becomes physically impossible to actually to do it, even if your page is as long as you want it to be. And think about 16. 65,000. All right. That's just another example of the function f of x equals 2 to the x. Ooh, melting. All right, how about this one? Did y'all ever see that Mythbusters where they took 2 phone books? Did y'all see that one? What they did is they took 2 phone books, right? So let's say I have two phone books. I get the first page, I fold the whole phone book over, I just lay the first page there. Then the first page of the other phone book and put it in. And then I fold the second page of this phone book in like that, and then the second page of this phone book in like that. And they did that for the whole phone book, all right? So you've got just page laying on top of page, both, what do you call it, the splines of the phone books are over here. And then said, how much force would it take to pull them apart? So they're not glued or anything like that, right? Try to pull them apart. They actually got 2 tanks and connected them together, and they couldn't pull them apart. Just from the friction of the pages alone. It's pretty incredible. All right, I'm sorry, I'm going off on a tangent there.
Oh yeah, that was.
Yeah, that's pretty cool. Maybe if we have 5 minutes, I'll show you my favorite Mythbusters video. But huh? What? All right. So next one. Let's do another bacteria problem. But this time, my bacteria does this. Starts here. And this bacteria is exceptional because it will triple itself every day. And let's just say every day again. What would my T table look like for this bacteria? Days and number of bacteria.
That's gonna grow really fast.
It's going to be fast. How many bacteria do I have at day 0? One guy. Day 1? 3. Okay, day 2, 9. So I didn't double, did I? I tripled. So day 3, 27. Day 4, I triple again.
54. Oh, not funny, but
Triple, 81. So what is the function here? Does everyone recognize all the numbers on the right-hand side? Not x cubed. 3 to the first power, 3 to the second power, 3 to the third power, 3 to the fourth power. So it's 3 to the x instead of 2 to the x. So our function is 3 raised to the x. Again, not this, okay? It is not f of x equals x cubed. That's not what's happening. Now, as you might imagine, this one grows faster than 2 to the x, doesn't it? Let's just go out to 10 just to compare it. At 10, where am I? We were, with 2 to the x, we were at 1,024, weren't we? Something like that? So 59,049. Really fast.
when you get to 21, it says eat time.
Yeah, so at 21, you're already blowing your calculator up? All right. And then what about a bacteria that instead of tripling itself every day, it split 10 ways? That'd be 10 to the x, wouldn't it? And that's probably more realistic. I mean, or that you have them, maybe splitting every couple of minutes, and that so it happens faster. So do you kind of understand the idea of exponential and just the idea that the bigger the number is in there, the faster it's going to grow? All right. Now we're going to do another example. The cutting page in half. All right, this one's going to be different, so make sure you pay attention to this. What I'm going to do is I'm going to start with a piece of paper that, let's say, is 1 foot wide. Okay? I realize that this is not 1 foot wide, but let's just act like it is. All right? And what I'm going to start with is I'm going to start cutting it in half and then measuring how wide it is. Okay? So I'm going to make a table. Here's the number of cuts. Here's the width. And I want my width measured in feet. So if I do not cut the page, if I have 0 cuts of the page, how wide is it? 1 foot. So far, that's looking pretty much like what we had already, right? With our bacteria. And with our folding the paper over, right? 0 folds, we had 1 thickness of paper. So now let's cut it one time and cut it directly right down the middle in half, right? So I cut that in half. Perfect cut, all right? 1, and how wide is it now? Half of a foot, right? Yep. Exactly. So I'm going to get rid of that 1/2. Now I have this much. That's half a foot, right? Now cut again in half.
1/4.
So it's going to be, second cut gives me 1/4 because it's half of a half, right?
Still, the denominator is just
Third cut. Well, that's pretty good. I'm doing good today on this. This is what? This is half of a fourth, which is 1/8.
Because Jack and Coke.
It's Thursday. Yeah. So now half again. It's a good day. I'm making up for my bad math earlier, like cutting this pretty good. And then I keep going, right? So what is happening here? I mean, notice the denominators, 2, 4, 8, 16. That's what we had earlier, right? But it's a fraction. So it can't be 2 to the x again. Do you see that each one of these, like 1/2 is 1/2 to the first power, isn't it? Isn't 1/4 1/2 squared? And isn't 1/8 1/2 cubed? And 1/16 is 1/2 to the fourth. So this function is actually what then? 1/2 to the x. Now, is this growing exponentially? I mean, is it?
No, it's increasing.
That's right. Now what we have is something that's getting smaller, but it's getting smaller very fast. So we would say it's exponential growth, but opposite. It's not growing, it's shrinking. So we call this exponential decay. Decay is when it gets smaller. Growth is when it gets larger. Well, you have decay in a lot of things in like chemistry, and like radioactive decay is exponential. Okay, so when someone on TV says, oh, exponentially, it could actually mean that it's going away also. It just depends on what your exponential function looks like. So we've had so far that thing in there, right, that's being raised to the x, we've had what? 2 in there, right? 2 to the x. We've had 3 to the x, and now 1/2 to the x. It turns out that you can have almost anything there, and it's exponential. But there's a couple of exceptions that you can't have. So now I think I'm ready to define what an exponential function is. An exponential function with what we call base b is defined as follows. Okay, here's the way we define an exponential function with base b. F of x equals b to the x. So the b is called the base. Now here are the restrictions on b. B must be greater than 0. So you cannot have a base of 0, and you cannot have a negative base. Also, b cannot be equal to 1. Why not? Why do you think you can't have 1? Okay, what's 1 raised to any power? 1 squared? What's 1 cubed? What's the square root of 1? It's cube root of 1, right? 1 to any power is still 1, right? So it's boring. It's a function. It doesn't grow. It doesn't decay. It just stays the same the whole time. So we just throw that out. We say that can't be, exponential functions, we just never let the base be 1. So any function where you have a number raised to x is called an exponential function as long as the number down there is a positive number and it's not 1. Got it? So since 1 is kind of like this critical number where like we can have stuff below 1, right? All the way to 0, and we can have stuff above 1. There's something very interesting that happens if you let your base be less than 1 and greater than 1. So I'm going to show the differences right here. If b is greater than 1, you will always have exponential growth. If b is bigger than 0, that's not bigger. bigger than 0 and less than 1, then you have exponential decay. Decal. So like when our base was 2, it grew, right? When it was 3, it grew. When it was 1/2, which is less than 1, it decayed. Y'all still with me? Okay, the last thing we're going to do here is we're going to graph these. Now, remember I said exponential functions are easy to graph? Like compared to like rational functions, easy? I think you'll agree once we do an example. Graph
We need at least 5 minutes at the end. Don't forget.
f of x equals 2 to the x. Now, look, when we had lines, we had ways of doing lines, right? We had y-intercept, slope, you found another point, you drew a line. When we had quadratics, we find vertex, x-intercepts, all that stuff, right? Polynomials, synthetic division, left behavior, right behavior, all that junk. Rational functions was a nightmare, right? All those steps. Exponential functions, t-table, like old school style sketching. That's the way we do it. Okay, we're just going to make a t-table, and we're going to graph some points. And I require 5 points. So everyone should have the same thing when you go to graph these. X goes here, 2 to the x goes here. Here are the 5 points that I will require that you put on a graph for your test. Now watch the way I do this. 0, 1, and 2, right? 0, 1, and 2. Now we never plug negative numbers in early, did we? But we actually can. And we're going to see that in a second. So you also need to try -1 and -2. Now you can't have a negative base, but you can plug in a negative number, as we'll see. So let's go and do 2 to the 0. So we're going to plug 0 in first. 2 to the 0 was what? 1. And then 2 to the 1 was 2. And then 2 to the 2 was 4, and I could keep going, right? 8, then 16, but that's the only ones I'm going to require. Then let's plug in -1. So we haven't done this. 2 to the -1. Isn't that the same as 1 over 2 to the 1? So I'm using a property back from exponents that x to the -n was 1 over x to the n. That if you ever had a negative exponent, you drop it down. Remember that thing? So if I have 2 to the -1, I drop it down as 1 over 2, and it's positive. It's not negative. So it's just 1/2. I dare you to go into Subway and order a 2 to the -1 foot sub and see what they'd say. That'd be a 1/2 foot. That'd be 6-inch sub, right?
I want to be working there anyway, so they
I've done that before, like HEB, asked for like 1/2 pound of something, like at the deli, you know. I'll just take like 2 to the -1 pounds, please. They're like, what? 2 to the what? It's just 1/2 pound, come on. 2 to the -2 would be what? 1 over 2 squared, which is 1/4. Notice what's happening here is that no matter what number we plug in, we're always getting a positive number out, aren't we? No matter what. So let's see how our graph behaves then. Since I know I'm only going to get positives out, I'm going to draw my graph like this. At 0, I should go up 1, right? So I'll say that's 1. So I have that point right there. At 1, I'm at 2. At 2, I'm at 4. And then the negative ones become a little bit hard to do, but we'll do our best, okay? At -1, where am I supposed to be? 1/2. So just go up to about right there. And at negative 2, where am I? A fourth, which is just slightly above the x-axis. Where would I be at negative 3 if I had done it on my table? Where would negative 3 have put? I'd be at 1/8. And then at negative 4, I'd be at 1/16.
Like a rational, so you have a horizontal
Exactly.
asymptote.
That's right. You actually have a horizontal asymptote on this function, but only out the left side. So what I get here, I'm going to draw a dotted at the end here. I'm going to draw a dotted, well, I don't want to use blue. I'm going to draw a dotted dash line on my x-axis like this. And then when I draw my function, I'm going to connect these. And I'm going to get closer and closer. Oh, man, I messed up. Ah, geez, that's terrible. So there you go. There you go, right there. And then what's happening to the right?
Gonna go up continuously.
It's just taking off, and it's going fast, right? So something like that. Now be careful. On the right-hand side, you do not have a vertical asymptote. Remember the vertical asymptotes forced you up and you couldn't go past it? These exponential functions keep going out to the right, but they just are like way out there now. With me? Okay. That is the graph of that exponential function. That's it. Okay? That a lot better than like 6 or 7 different steps? T-table, graph. Just make sure you note that you'll always have a horizontal asymptote, and you'll always have the other side going off to infinity. I still have 10 minutes. Okay, you think with what I gave you, you could graph a couple of these for homework? Okay. All right, well, I'll see how you do. So this will be your homework. I want you to see if you can graph the following. F of x equals 2 to the x. No, we just did 2 to the x. 3 to the x. 2 f of x equals 1/2 to the x. Number 3, f of x equals 2.718 to the x. You're just plugging in points, right? That's it. Make sure on these graphs you do exactly what I did there. Just draw your little table, do at least 5 points. If you want to do more points, you can. It's up to you. And just be as precise as you can. It doesn't have to be perfect, all right? Now, how's our attendance here today? I think we're going to need to do attendance. Let me see if I can find this real quick. I'll show this to you. Okay, here we go. So check this one out. Hopefully it'll come up here. All right. All right, look, I'm cutting y'all out here early, but let me just at least show this to you, okay? Yes, thank you, thank you. Silence, please, silence. Let's see if the speakers work or not. It might be loud, so let me turn this down real fast. Speakers up there aren't muted. It's not muted. Where?
Look on your screen.
I know, I'm trying to unmute it. All right, well, we're just going to have to listen to it off my laptop. You really don't even need to hear it. I mean, all right, here we go. So they have this car. So what they're trying to do is basically see what happens if you could have two cars hit each other and or smash two trucks, smash a car between, and basically leave nothing but just like smashed car, like just flatten it. They tried it, they couldn't do it. So instead, what they're doing is they're putting a car, and then they have a big concrete block behind it, and they have a piece of metal, and they're going to fire it down a sled, like a track, into the car and smash it up against the concrete block. Okay, here we go. Speed of sound. That's how fast it'll go. I'm going to try and get to the slow mo part of it. Oh, here it is. Okay. I'm going to fast forward for you here. Okay, here we go. Okay, I want you to notice something here when they show this. You're going to see the actual paint from the car vaporize off of the car. So you'll see like a red cloud. It's the paint coming off the car. It just gets vaporized. See the red up there? That's the paint of the vehicle. Here we go. See it up there? I mean, that is some force when you can remove the paint into like its almost atomic state off the car, remove it from the metal. That's pretty fast. These guys are funny. Okay. All right. Y'all have a good weekend.
That was bad.